Okay, picking up where we left off, we were just talking about the bond line structures, how to draw them, how to read them, and now we're going to go over a few different scenarios where there's slight variations in the rules. One thing is we have to remember that what I was just talking about is when we have atoms that are fully neutral or molecules that are fully neutral. That's not always going to be the case. In the middle of a reaction, we may have a positive or a negative formal charge on carbon, and that's going to change the assumptions that we make when we draw our bond line structure. So keep in mind the rules that we were talking about, that's for neutral carbon atoms. But sometimes we can have a positively charged carbon, and sometimes we can have a negatively charged carbon. These have new names. Okay, so a positive charged carbon, we're going to call it a carbocation. So it's like carbon plus cation, we just call it carbocation. And then down here, we've got, for example, a negatively formal charged carbon. This is what we call a carbanion. But starting with the carbocation, rather than having a carbon-hydrogen bond, basically in its place has an empty p orbital. So this carbocation here, for example, has 1, 2, 3 bonded atoms, no lone pairs. That's an sp2 hybridized carbon, and that means it has an empty p orbital. Here, if we have one that's in the middle, so this one has 1, 2 bonds drawn, it's got a positive charge. That means it's a carbocation, so it's got an empty p orbital. That means it's missing 1 hydrogen here. So again, the way that you can think about it is basically if you see a positively charged carbon, that's going to be an sp2 hybridized carbon. Similarly here, this terminal carbocation has a positive formal charge. It's sp2 hybridized. So we know it has to have 3 bonds. So 1 bond is shown. The other 2 must be 2 implicit hydrogens. On the other hand, if you have a negatively charged carbanion, a negatively charged carbon, that's the carbanion, that's going to have 3 bonds as well, but also have a lone pair. So this carbanion is also going to have, is going to be sp3 hybridized rather than sp2 hybridized. Just one thing to keep in mind with that. So the reason that we want to state this is because formal charge is going to dictate the reactivity of the different molecules. So very briefly, like we just need to be able to quickly identify formal charges for different representations. The way that you can always do this is just remember what is the valency of the atom that you're looking at. So for example, we mentioned that carbon is tetravalent, oxygen is divalent, nitrogen is trivalent, sulfur also here should be, sulfur is a little different, that's in the period 3, so it has a little variable bonding. We're not going to worry about that so much. But for example, here we look at oxygen. Oxygen is divalent. That means it should have 2 bonds, but we actually count 1, 2, 3 bonds. So rather than having 2 lone bonds and 2 lone pairs, now all of a sudden it's got 3 bonds and just 1 lone pair. In terms of its formal charge, like what we did in the last chapter, well, it's got 1, 2 atoms, or 1, 2 electrons, and then 1, 2, 3 electrons, so 5 total electrons assigned to it. We know oxygen should have 6, so if it's missing an electron, that means it's got a positive formal charge. Go ahead and go through this molecule and see if you can identify the other formal charges here. On the next couple of slides, we're going to go ahead and talk a little bit more about this and give you kind of rules that you can always use to help out. Okay, so real quick, let's go over this real quick. I hope you pause the video and give it a shot, and then let's go ahead and actually draw them in. Now I gave you this one. This is an oxygen that's got 3 different bonds, okay? And we know oxygen should be divalent, so it's got a positive formal charge. Here, this oxygen is divalent, it's got 2 bonds, no problem. Here, this oxygen has 1 bond and 3 lone pairs. That should be a negative formal charge there. Nitrogen is trivalent. So nitrogen, remember, should be, it should be that it has 3 bonds and 1 lone pair, but here we count actually 4 bonds instead. So if we were to assign it, we have 1, 2, 3, 4 valence electrons for this nitrogen. It should have 5, so that means this has a positive formal charge as well. Now the last one that we would have to do is we'd have to do this sulfur here. So we just have to do it the only way that we can, which is just count up the number of electrons that are assigned to it. It's got this lone pair, and then 1, 2, 3, 4 covalent bonds. So that's 6 total electrons. Sulfur is in the 6th group, 6A. So that seems fine. So no charge there. All right, let's go ahead and clear the drawings and move on. Oh, finally, this nitrogen down here. Again, nitrogen trivalent, we count 1, 2, 3 covalent bonds. It's got a lone pair. So that seems fine. It should have a neutral 0 formal charge. Okay, so one thing is, a lot of times this semester, you're going to see molecules or bond line structures that include the formal charge, but do not include explicit lone pairs. That's because, again, just like with drawing the hydrogens, it gets messy if you have to keep drawing lone pairs on everything, and it's easier to misinterpret than it is just to draw the formal charge and then have the assumed lone pairs from there. So for example, this is what's called the ethoxide ion here. This ethoxide ion gives a negative formal charge on the oxygen. Well, if there's a negative formal charge on the oxygen, that means that in place of one of its bonds, it needs to have a lone pair. So it has its normal 1, 2 lone pairs, and then it has a third lone pair that occupies its other, basically gives it a complete octet. And that's what we actually see when we draw it out, sure enough. But more often, you're going to see things drawn this way rather than this way. Okay, and so here again is just going through when we have a formal charge, what does that mean? Or how are we gonna read these formal charges? So, okay, so if oxygen has 7 valence electrons, that's what we were just looking at here. That's 1 bond and 3 lone pairs. That's a negative formal charge. So just keep in mind, the way this is usually gonna look is something like this. You have a negative formal charge on an oxygen, that's got 3 lone pairs. When it has 6 valence electrons, that's neutral. So that's 2 bonds plus 2 lone pairs usually. And then finally, if it has 5 valence electrons, that's 3 bonds plus 1 lone pair. That's going to be when you have a positive formal charge. So here, that's this OH2. This oxygen has 2 bonds to H and then 1 bond to carbon. That's 3 total bonds. It's only going to have 1 lone pair, and it's going to be positively formal charged. So again, you can keep up with these in your book. These are on the Skill Builders 2.4. We're going to have one sample exercise as well that covers all of these here at the end. But let's look at the patterns for the next ones as well. So nitrogen is next up. When nitrogen, if it has 2 bonds and 2 lone pairs, that gives it 6 total valence electrons, right? 4 from the lone pairs plus 2 from the covalent bonds. That's when nitrogen has a negative formal charge. That's what this looks like here. So it's an NH minus. So just keep in mind, negative nitrogen, that's 2 bonds plus 2 lone pairs. If you have 3 bonds and 1 lone pair, that's 5 total valence electrons, 0 formal charge. And then beyond that, another common situation is when nitrogen actually has 4 bonds. So 4 bonds plus 0 lone pairs, that's 4 total valence electrons, and that's a positive formal charge on nitrogen. Okay, so go ahead, make sure you practice that formal charge identification. And then after that, we're going to talk about 3 dimensions. So the molecules that we've talked about so far, it hasn't really mattered yet the orientation in 3-dimensional space, how the hydrogens are oriented. And that's because all of the molecules we've talked about so far have some degree of symmetry. But there's going to be a time this semester in the very near future where we're going to talk about molecules that are asymmetric. And when we talk about molecules that are asymmetric, we need to be able to draw them, or we need to represent them on our piece of paper or on the screen share here in 3 dimensions. So the way that we do that is by using dashed and solid wedges rather than just like the straight bonds here. So like, for example, here we have a cyclic group here. These here are all in the same plane. So the ones that aren't dashed or solid, just like the normal bonds, like what we've been drawing for the bond line structure, those are all in the same plane. Think of those as like flat compared to one another. They're in your paper. Okay. So then we have the solid wedge and the dashed wedge. So the solid wedge, you can think about that one as like coming out towards you. So I'm going to try to do it out of the camera. Like here, this is like going out at you, okay? Whereas the dashed wedge, that's coming into the screen towards me. So again, say this one more time. This Solid wedge, that's going out of the screen towards you. And then the way it looks to you, this is, I'm in the screen, right? So this chlorine is going into the screen because it's got the dashed wedge there. So that just tells you basically the orientation in 3 dimensions. So we want to like make sure that we understand how this works. So make sure to give this some practice on the sample exercise and in your book, your skill builder in your book. There's a few other ways that we can do these 3-dimensional structures, including the Fisher projection, the Hayworth, and then we have a bicyclic structure that we'll talk about as well. The Fisher projection we'll get to when we talk about, I believe, saccharides in the future. So just keep that in mind. These are really important for biological compounds. Okay, so that covers that. Again, get some practice on the formal charges and with the 3-dimensional drawings, and I'll see you on the next lecture.